Every day, the Earth experiences a potential energy that pulls it toward the Sun with a force that grows stronger the closer the Earth is to the Sun. But in 4.5 billion years, the Earth still hasn't fallen into the Sun's fiery depths. Why is this? It's because of a beautiful concept called conservation of angular momentum. Because the Sun only pulls the Earth inward, it can't change the angular momentum, or spinniness, of the Earth's orbit. So when the Earth is closer to the Sun, it travels faster and can then move farther away. And when the Earth is farther away, it travels slower and can then move closer. So if you just consider the in and out motion of the Earth, it's as if there's a potential energy acting on the Earth, one that's pushing it away from the Sun. Through math, we can model this potential energy and its relationship to the angular momentum, so we say that our potential energy effectively has two competing terms. One that pulls the Earth toward the Sun and one that pushes it away from the Sun. This effective potential energy is interesting because it has a minimum, and depending on the values of the various constants, it can take on a very asymmetric shape and produce orbits that vary wildly. The orbit that a planet takes on depends on the amount of total energy it has. Consider, for example, Halley's Comet, which once every 75 years comes in from 3 billion miles away to pass within a mere 54 million miles of the Sun. For reference, the Earth is 93 million miles away. These 2 points of farthest and shortest distance are called the aphelion and perihelion of the orbit. These numbers for Halley's Comet differ by a whopping 5,500%. When an orbit has a very different aphelion and perihelion, we say it has a high eccentricity. In fact, Halley's eccentricity is so high, it's just a few steps away from leaving the Sun and never coming back. Now, fortunately for us, the Earth's orbit has a low eccentricity, meaning its aphelion and perihelion differ only by about 3%, so we don't experience a drastic shift in temperature due to our orbit. But still, it's very important to calculate these 2 points for studying bodies orbiting the Sun, asteroids passing near the Earth, and eventually evaluating the habitability of exoplanets. So, our goal is to create a code which can take the two masses, the planet's angular momentum and energy level, and calculate the aphelion and perihelion of the orbit. The aphelion and perihelion of the orbit occur when the planet doesn't have any more energy to spare getting further away or closer to the star. If we plot the new potential energy and draw a horizontal line representing the total energy of the planet's motion, then we're looking for where those two intersect. We're going to do this with a pretty simple but surefire approach of taking a region, dividing it in half, and figure out which of the two halves holds the intersection. So for example, let's suppose the aphelion was somewhere in here. That means that the point on this end is below the total energy, and the point on this end is above the total energy. If I cut the region in half, I can evaluate whether the middle point is above or below the potential energy. Since it's above, I know the minimum has to be in the left half, and I can ignore the right half. Then I can repeat the process, making the region where I know the aphelion has to be smaller and smaller. So, starting in the next episode, we're going to encode this process and test the results on Earth's orbit. Thanks for watching. See you next time.